This week we're covering reflection and interference and all the different ways that that kind of shows up. And that means we're going to talk about several different things. We're going to talk about wave propagation. We're going to talk about reflection as a separate thing. We're going to talk about interference and what that really is. We're going to talk about bass traps because bass traps are a way of designing interference to benefit you. And then we're talking about resonance in enclosed spaces. Kind of variables we're dealing with, there's distance waves traveled, there's frequency, wavelength. I mean, you've named all these. Phase of a wave, I'm introducing a new one there. Talk about that a little bit. Wave velocity, incident angle, reflected angle. These are all pretty straightforward and simple for you guys at this point. So let's talk about a traveling wave. So we got a wave that's moving along. And in here, it's a function, if you're at any one point, it's a function of both time and position. And I put this little term up front just to kind of remind you, as the wave propagates, it attenuates as it spreads out. Um, but that we're not going to worry about that piece so often. Just that's one of the factors here. And so we've got this equation you may have seen before, may have typed before. You got 2 pi times the frequency times time minus 2 pi over lambda, the wavelength, times distance, and then a phase angle, which is a new thing. And this is basically how many cycles have you gone through and how many wavelengths have you gone through. Those are what those two terms really come down to. How many cycles have you gone through? How many wavelengths have you gone through? Um, and um, the wave propagating along some direction. And we just call that direction X, whatever that is. Well, when you think about this in the context of speaker placement in a concert hall in particular is where it's enough of an issue. You got your speakers back at the stage, and then somewhere out in the hall you have some other speakers. Well, if you simply timed these so that the sound came out of this speaker at the same time that it came out of this speaker, then the sound from this one would be right about here when this is here. Right? And so what people are going to hear is going to be muddled back in here because the timing from the different speakers is going to be so far off. You want that timing to be as close as you can actually get it. And so what you have to do is you have to delay the speakers out here. And you have to delay them to give the time from this speaker to get to here so that when the sound starts leaving from these speakers, it's all together headed out. If you want well, we'll talk about reflection next. All right. So this is the basics of you got to think about when you're putting speakers out in a large space and distributing them. You can also imagine, see this in one of the problems, if you don't have these speakers, but you're here on a football field and you're talking into a microphone, you say something, and then sometime later you hear it. Some people really struggle with this and have to have earplugs every time they're out on in a big setting like that, and they're speaking and listening to themselves on a delay. And that delay is just determined by the velocity of sound and how far away you are. So the distance equals velocity of sound times time. All right, reflection is really simple. When you look at the incident and reflected angle, the angle between the incident and what we call the normal, perpendicular to a wall, this is a wall here, sound hits the wall and reflects off, it actually comes off at the same angle it went in at. So it goes in here and comes off at an equal angle. That's really it. A reflection angle, your reflected angle equals your incident angle. And you'll see if you go into some of our concert halls, and particularly the small concert hall at the Bologna Center, you'll see the walls are textured. And the reason the walls are textured is so that the sound hitting the side of the wall breaks up and goes all kinds of different directions instead of coming off as a coherent signal. And so, that's one of the reasons, one of the sound treatments in that room is the texture on the wall to break up sound that's reflecting off so that if you're sitting out here in the audience, you're not really hearing the reflection off the wall. You're just hearing the sound that comes directly from the stage. If we were in class, my voice typically is low enough that I can hear the reflection of my voice off the back wall of most of the classrooms. And so that's one of those things you can just, as I speak to you in class, if the class isn't full, I can hear that reflection. What does that lead to? Well, let's talk about two different waves. And here we have two different waves and the phase angle between them, and we're at some given location, so we're only worried about time. The phase angle between them is 0. So they're in phase, and you add these two waves and you get a wave that's simply double. All right, that's straightforward enough. Well, what if they're off by 90 degrees, right? So they're not quite in sync. Well, now you have a wave. It's got a slightly different phase from either one of them, and it doesn't peak all the way up where it was not all the way up at 2, it's down under 1.5. So that's at 90 degrees, where they're, or in this, it would be pi over 2, right? Now let's move to 180 degrees, and what happens? The waves are completely canceling each other out, right? Completely canceling each other out. Okay, let's simulate something a little bit more realistic. So one of the waves comes at you directly. The other wave is reflected off of something, and so it's attenuated a little bit. But when it arrives where you are, it's 180 degrees off. And look what you get for the sound. You've subtracted off most of the direct wave with the attenuated wave. And this is barely attenuated. It's at 90% of the original signal, right? And so you get just a little quiet ripple. Where is this important? Well, let's consider our room. You've got a speaker sitting here, and the sound goes and hits the wall and comes off. You're sitting over here, and the sound comes straight to you. Well, this path from here to here is longer, and then this path that goes straight. That phase difference is due to the difference in the path length, right? The path length gives us a phase difference. It starts out at the same phase here, but over that distance, this has gone through more cycles or more wavelengths than the direct path. And so if you look at the example I have here, you got 4.656 meters and 3.24 meters. That's the long path. 6.76 meters is the short path. That's a whole meter difference in path. Right? That adds up to a difference in what's happening out here. And notice, right? Completely destructive if the path difference is half a wavelength. Completely if it's an odd multiple of half a wavelength. Completely constructive, it's an even multiple of half a wavelength. Right? So our destructive interference, we can do it like this. 2n minus 1 gives us all the odd numbers. Well, that means in this example up here, that if you're sitting here, then 166 hertz is gone, right? And 498 hertz is gone, and 800 something hertz, right? So you have these given frequencies that are being filtered out just by the geometry of the room, right? Just by the geometry of the room, we're filtering out different frequencies. And off a little bit from this, right? It's still canceling out some, right? So in a range around this, you've actually depressed the signal here. This is why how you set up acoustics in a room is so important, and why sometimes there's only one place to sit and listen to a system, right? It's designed for a spot. If we were face to face, I would play a single tone for you, a pure tone off of a computer out of two speakers sitting in the room, and you would walk around the room and you would hear the points as you walked around the room where that tone gets depressed because of destructive interference. All right, that's it for this piece, because I don't want this video to be too terribly long. We have just a small little bit left to go, and I'll do that in a separate video.